Right, one of the applications for parametric equations is horizontal motion problems. Now these algebraically are more algebra 1 type problems, maybe even pre-algebra, no, probably algebra 1 because of the setups. So solving them isn't going to be too challenging, but we are going to look at how you could put them in the calculator. So I'm going to show the calculator in the video, but we'll most likely show it in class again to make sure everybody's on the right track with that. Okay, so in this situation, we have Tanya, a long-distance runner, runs at an average velocity of 8 miles per hour. So Tanya's equation is just going to be I'm going to call this x1. So she's going horizontally on the x, 8t. Now, ideally, Tanya and then the car, because the car 2 hours later, after Tanya leaves your house, you leave in your Honda and follow the same route. We're going to put them on different paths. So I'm going to put Tanya on y1 is equal to 2. And then the Honda I'll put on a different path. Ideally, the car is in the street and Tanya is probably on the side. So they are on slightly different paths. We want to show that on the calculator. That's the reason for the y's. And then the Honda. Now, it's important when you put in the time, you leave 2 hours later. So time is going to go in the parentheses. Distance is going to go outside. So time 2 hours later. So we do t minus 2 because you don't want your path to start until 2 hours after Tanya has left. So you always do subtraction on those. Now I'll put I'll put the Honda on a different path. So I'll do 2 and 4. You can really pick anything. You could do 1 and 3. You could do 1 and 2, although I wouldn't put them that close together. But you can pick any numbers for these. That's just the path. So whatever you want to choose. I'm probably going to go with 2 or 4. Make y's different. So on different paths. And this is for viewing purposes only, really. Now, the actual how long is it going to take for catching up to Tanya? You set your equations on your x's equal. So you have a very basic algebra equation to solve. And that part of it is not the parametric part. But we are going to solve these situations and then talk about the windows we will use for graphing purposes and simulate the motion. So we get t is equal to 2.5 hours. Now, usually I'm a little more specific. How long will it take for you to catch up to Tanya? It's really from when you leave. So if you do 2.5 minus the 2 hours, it will take you 0.5 hours, or you could put 30 minutes if you want. To catch Tanya after you leave. So the 2 hours that you were sitting at your house don't really count in this situation. And again, those kinds of things, I'll be a little more specific when I ask the question about how long it's going to take a person to catch up or vehicle or whatnot. Now, if we're doing this in hours, I'm going to do 0 t min. I did a t max of 3. I make it a little bit bigger than the actual time. The t step can vary. I'm going to do 0.005. You could start with 0.01 if it's too fast. You could do 0.001. That might be too slow. All of the beginning ones are going to be 0, so that's easy. And then I'm going to do 8 times 3 equals 24. That's going to give me my, I don't know why I wrote it there. That's going to give me my x max. And I'm just using the t value that I got to figure that out for my window. And then my y max, I'm putting 6. You can kind of keep this standard depending on what you pick for your y1 and y2. So that's based off of this stuff that's going on up here. right, so I'm just going to simulate the motion on the calculator. I'm going to switch to parametric mode. Whoops. I'm going to go to my y equals. Now you'll notice it changes. So if you don't already have your calculator in this, so I'll put 8t and 2, and then for x2 I'm going to put 40 times t minus 2. So the exact same equations that I set up. And 4. Again, the reason for that is they're on different paths, and you have to put in a y in order to get it to graph. The window setup is very important for these to get the right values to see the actual motion. So again, 0, 3, 0.005, 0, 30. So I already kind of decided on these. You kind of almost have to solve the problem to set these up. Now on the computer calculator, it does go a little bit faster. So now I'm going to hit graph, and it's going to show the motion. So there's Tanya running, and then all of a sudden, here comes the car. Okay, the car does not come yet. I'm going to hit the on button, stop the graph. Forgot one thing in the mode. We need to put it on simultaneous, not sequential. We want to see them happening at the same time. So go over and make sure you select simultaneous. We're going to do the graph again. So I'm going to hit graph. There goes Tanya. And the car should be coming. And there goes the car. And then the car catches up and goes past. Now, assuming that you want to see the actual point where they catch up, you could go back to the window and put it on the actual solution of 2.5. And then when you graph, you will see that they will be even at that point to show that that's where you're catching up. Now, this is a pretty good speed. It's not too fast, not too slow. A little fast for the car, but the car should be faster. So you see, I put it on the actual solution. It does stop at that time. Okay, that's one scenario. I'm going to actually do a second video for the second scenario so this doesn't get too long. And you can try mess around with the calculator a little bit to get the simulation if you want in between videos.